chance you can read continuity.
Didn't understand?
Things that are,
Okay. So the divergence of velocity is 0 for incompressible fluid. Okay. Here you just have to derive Euler's equation. Few lines derivation. This is the velocity field given in two-dimensional space with x, y, and z components. And the pressure is given as well, scalar quantity. The fluid is stationary. That means d dt goes to 0 in the equations of motion. Okay. It's a stationary fluid, which means no time dependence. Okay. What do these parameters represent? What is the fluid? It is water or nitrogen?
fluid what?
Fluid. Fluid is either water,
Okay.
water or nitrogen. You have to find out. Okay. I guess you sense how you find it out. If you try to determine the viscosity of this fluid, given Navier-Stokes equation we derived in last lecture.
What is the word in question 2?
Last word?
In question 2.
Question 2. Fluids. Okay, I think my writing is still not improving. Okay.
The point that we didn't define Navier-Stokes equation for principles.
We derived general Navier-Stokes equation and then we derived it for incompressible fluids. It's incompressible fluids.
Could
But
we have the
we have for compressible fluids as well.
could we have the equation for the general Navier-Stokes equation? So if we needed an equation for that.
You don't need the general one here, but if you need it, I will tell you the equations. But first try to write it because it's just one extra term in Euler equation.
Yeah, just
And the same is given here, but this here the velocity field is one-dimensional, and pressure is also one-dimensional, just x. And then here the important thing is this one, which we will study today. If you assume v dot grad v equals 0, that's part of today's lecture. It is true for small Reynolds number having fluids. But for the timing, you just put this equal to 0 in the Navier-Stokes equation and find the viscosity. Eta. This is 40. Okay. If anything is not clear, you can ask me. And please write your name at the top. This will not be a part of the grades, but it's important for me to understand who understands what. You will need this here. The first question. Here A is a scalar and B is a vector. This comes where it's rho V in the continuity equation. So you need that one.
Did you say A is a scalar?
In this equation, A is a scalar. It's a general identity. A is a scalar, B is a vector.
So if
always zero?
No.
Oh,
It's constant though.
No, it's a scalar. It's not constant. It's a scalar means it doesn't have direction. It's a scalar quantity.
We could just say that since rho is constant, we can take it out of any derivatives.
You have to, but I just wrote the general identity. You can do whatever you want. This is a general identity. Yes.
What are you asking?
Question 3. Okay. A velocity field is given. Velocity field V is given with x, y, and z component. And pressure is given. If the fluid is stationary, then you have to find out which fluid it is. It is nitrogen or water, one of the two. Either it is nitrogen or it's water. Use the equations and find out which fluid it is. If you cannot do it, ask me, but you should be able to do that.
what is the parameter that the question refers to? C?
See?
In 3I, what is the parameter? Which
These are the parameters. Velocity and pressure are the parameters given.
Can you answer privately for each student? Because
Okay. I thought these are general questions. If anybody else can talk. X and Y components are given.
I understand that this is completely like deduction. It's just the formula I get from first it's not physical.
No, it's not. Find it out, please. Try to find it out. Is it left hand side? What's the pressure, and then you have to integrate it. In third question, you have to use this Navier-Stokes equation. Remember, or I have to write this.
Just maybe the term that changes the
Okay, I'll write it. Okay, this is Navier-Stokes equation. Use this. If you ignore the last term, it is Euler equation. For incompressible fluids.
it's capacity minus.
Yes.
Yes?
No, no, but
X and Y coordinates. A is constant. Right side, it is Navier-Stokes equation. What is that in last question?
Yeah, what of it?
All of that. parameters B and P.
I'll just explain what they are.
These are the parameters given, right?
Just explain what they are.
The question is there. Fluid is water or nitrogen? It's question one. Okay. This is what you have to find. Okay. This is the question. You didn't get the papers? Yeah. write some hints for you, people who are not able to get it. This is already equation. This you will get from here. Convert this into volume integral. Okay. There's a reason I will explain it. It's not zero. Divergence.
X, Y.
Yeah. Divergence. That's what I can do. I can tell you, but I just can't. We're not very straightforward. Pressure there will not be minus sign. But pressure there will not be minus sign. With pressure there will not. But in the equation there is a minus sign.
Yes, and this and this are the same. So it can be this equals minus this.
made an error here. Did you attempt question number 3rd? I forgot -7. Okay. Just did this. Sorry for that. Okay, yes. Sorry for that, I made plenty of mistakes. It is okay. Did you attempt this question? Anybody missed? I'll give you extra marks. Okay, sorry for that, because even in that case it can be solved, but the conclusion may not be what I want you to understand. Is that okay?
Actually, I think it can be solved that way.
It can be solved that way as
I
well.
got
But you will get a
nothing, so
no, viscosity will be complicated.
oh,
But it's very
Okay.
simple. It's very simple. I didn't mean it to be a very complicated question.
Yeah, but why do not have bulk viscosity now?
Hmm?
Bulk viscosity should be. Assume it to be 0 at the moment. Okay? It can still be 0 for gases. Yeah, it can be 0, it can be given. Right.
It's also incomplete.
So you mean that we need to answer both small 1, small 2 for the
Hmm?
problem. For 3 there are 2 questions,
Yes.
and for 4 the same, or
4 is just viscosity eta. You have to find eta. Eta, while you assume that bulk viscosity is 0. Okay. It's a guess for that there is no bulk viscosity, or it's negligible rather. And in what?
I have a question for the
Yeah, it's
top. It's 8 times.
ax square.
Yeah.
A, not 8. A,
8 times
x square.
x squared.
why do you assume this?
That I will show in today's lecture. Okay. You cannot. It is not 0, but why it is? It can go to 0 for small Reynolds number. I will show you. That we will study today. But for the time being, you assume it to be 0, and I will show you why it is 0. It is not 0, but it goes to 0 compared to the last one. Yes. So that's it. Yeah. Yeah, so give it viscosity. You cannot determine. It's undetermined. The second conclusion is you found out that this is satisfying the Euler equation, right? Fluid that satisfies Euler equation, its viscosity is 0. Okay? So that means it does not have viscosity. It has 0. Okay, so conclusion is from the equation you cannot find it out because it is 0, 0, 0. But any fluid that satisfies Euler equation, the viscosity does not have viscosity. Okay? Therefore, the viscosity is 0. It's just a matter of interpretation. It is not bad. It is not bad. Why it is not bad? Find the divergence between the divergence of the first question, divergence of visible and invisible fields. If you find the divergence of the equation 2, what do you get? If it is 0, it's not. If it is negative, it's not. Just for you. Okay? And it's not bad.
What about the correlation between velocity and pressure? Correlation between velocity and pressure.
What is the correlation?
Forgot.
Why there is a correlation between this? What do you mean the correlation?
Like F is equals to NA, the correlation between force and acceleration. So there's a correlation between velocity and pressure. Check that.
I think for that, F equals ma, when do we get it? Right? But little bit F is integral of F. Right? Convert this into very integral. Divide by Just use the term for eta and apply it for 0. Just use this equation that I wrote there. The one I wrote. Yeah. Yeah. Because I write psi is equal to 0. For this case, at the end I have written psi is equal to 0. There is no bulk viscosity. Okay? So force yourself to use the equation which I wrote there. calculate the viscosity in last equation? Did anybody calculate viscosity in last equation? Did you calculate eta using this equation here? What did you get?
What's the time?
Rho will cancel. We have rho here, right? Rho will not come here. We have rho here. You have rho here in equation, and you have rho here. So this will cancel.
No, but it's rho times 0.
What's rho times?
Yeah.
The whole thing cancels.
Ah, right. Okay. Then it will turn out to be in the form of rho. Okay.
But it's actually good.
Yes, it is.
That's fine. It's just a minus.
Minus is okay. Let's bring it over here. Yes. I think there's a problem. What do you get? What question? Okay, there is one more error. Many errors. I'm sorry for that. Pressure cannot be negative. It's just that I just made this question paper today, so make 20 errors. Pressure is positive because X is always positive, so it cannot be defined negatively.
Let's go for now question number 2. This is what we just said.
That you have A. It's fine, still pressure cannot be negative here. You will get negative viscosity here. This is why this expression is always it was positive there, but while typing I made a mistake. In the equation. Oh, that's no, that's not nice. It's 40 rho AX. Assume V dot grad V equals 0. Why we assume this? This is I'll explain in today's lecture. Eta. Only eta. Use the equation that I wrote there. Equation 4. Yes. Question 4 also, it's both are stationary fluids. In question 4 also ddt is 0. It's always 0. Question 2. Question 2 is okay. I'll do that. Okay.
What you say? Dx let dt is 0. Question 4. Dx let dt is 0.
ddt is 0. It's the first term in the Navier-Stokes equation.
dv dt is 0.
ddt is, yes, wherever ddt is coming. Convert it into derivative. Minus gradient of P ratio plus eta del square of Laplacian. Yes, we don't get it. Okay, so I tell you, the first part of 3, you have to find it in whatever nitrogen. That means, in the first question you see, the divergence of P is 0. In the first question, if the divergence of P is 0, let's say this is compressible. So you have to find the divergence of P in the question 3. If it is 0, it's what? It's not 0. Yes. That's what you have to think about.
I just missed the first question. I don't remember.
This is written in the first question.
Yes.
I've written it again. You don't need to follow. Okay, yes. All of these parameters we present. Fluid is water or nitrogen. You just have to find in question 3 what is which fluid it is, by water or nitrogen. That's it.
Which fluid was the fluid?
Which fluid? Question is only this one. Okay. So you don't have to study what I do sometimes. I will start with this. Everybody is done? Attempted? First of all, just to see if you can find the proper way to do things or not. Okay? Attempted all questions?
Just not sure.
You attempted.
Yes.
Without asking any question, you attempted. It's an achievement. If you guys are done, then we'll solve all the questions. Everybody is done? give me the sheets and then I will solve all the things for you so that you understand. You wrote your name? Write your name at the top. Whatever you do. Okay, let's solve this question. Alright, those who did not understand the questions or missed something or did not understand any of them, we'll just go through all of them step by step. I'm giving you assignments and you are doing a good job, but the problem is when you solve in front of me, I can see if you know the logic or not. Okay? So I see some people are getting stuck somewhere, that I can help you. So, I will give you the answers now. We'll solve it. Okay? Okay. So the first question, you have to show that the divergence of V is 0. It comes from everybody had attempted it, right? I'll do it here. This is from the question of continuity. If you open this, okay, for incompressible flow, you have this to be 0. The density does not change with time. Okay, and the gradient of density is 0. It doesn't change its space as well. So this time is 0, density is non-zero, so this divergence will be 0. This is the basics of Euler equations and basically this continuity equation. If you are sleeping at night and somebody tells you do this, you should do it in your sleep. Okay, Euler equation. Some people were stuck in Euler equation as well, which is a bit surprising to me. Euler equation is nothing but Newton's equation. F equals ma, which is m dv dt. Everybody knows this. But for fluids, F is equal to the surface bound with surface area F. The force is minus of surface integral of pressure within the bound surface. You convert this into volume integral, and this is the volume of the whole surface. Okay? If you find the force per unit volume, which is basically kind of force density, it becomes rho A equals simply minus of now A is dv dt, which we found out as dv dt plus v dot grad. Okay, use this to find out. This is already question. It's just 2 lines equation. Some people got stuck in that as well. So you are not expected to do it in sleep, but if you are awake, you should always be able to do that. Okay? These are very fundamental of fluid dynamics. After 20 years, you will forget Stokes' law, whatever we derive with viscosity and everything. But some child will come and ask you about fluid dynamics. This is what it is. And the third question. Now I show you how mathematically it was done. You have to find out whether it is water or nitrogen. What did you find? Which is that? You solve it, right?
I wasn't quite sure what the question meant, but if it's about the compressibility, then it's like what?
That's it. So if you find the divergence of V, like this one. So whatever we derived in first question, you just have to derive it from here. The divergence of V is minus minus and then it turns out to be 0. So this was satisfied for this. Water is incompressible fluid. We said it many times during the lectures.
The problem is we derive the divergence equals 0 from incompressibility, but can we do it from the other way? We derive incompressibility from the divergence. It is good proof or
Even at the stationary, yes.
I didn't understand. Divergence is a good proof.
He asks if you can prove it the other way.
Other way means what?
Given that the divergence of the velocity is 0, show that it is incompressible.
Yeah. Put it in the equation. Continuity. Put in the equation of continuity. Whatever is not done, right?
So it will be the stationary assumption for that.
maybe it's more conditional.
Okay, so this is the equation of continuity. If you put divergence of V equals 0 here, what you see is yes. Yes. So here you see, in order this to be 0, the density cannot have a gradients. Now you cannot have a physical argument where density can change with time but not with space. It requires density has to be constant over the space or time. Now we can think about it, is there a condition where the first term is satisfied and the second term is not? That I have to think about. You can also think about it.
That expression itself can be right without the density to be constant.
Why?
Because it can be a relation between space
Yeah,
and time.
that's what I'm
But
saying.
here comes the stationary assumption.
No, this is true
No?
for even non-stationary fluids. So this we will give a thought. It's a good question.
Are you sure?
We will give a thought. I'll think about it. And we'll talk about it more. But here what it implies is that density has to be okay. It's a very good question. Yeah. Very good question means there's something to think about. So this is 0, but maybe both the terms are not 0. It can be gradient of density and time dependence. And think about it. I never thought about it. Okay. keep it in mind.
Isn't this just the whole differential of
It is a whole differential of rho. It's del dot del t.
It's like saying the d rho is
Yeah, it's v dot grad kind of rho. D rho over dt equals 0. It is something like that, but still you have to give a thought. It's a partial differential.
yeah.
So the total derivative is anyway 0. Density cannot change with time. Given that, if something is missing, you didn't do it. Okay. Alright. And then in the third equation, we just use one more term. Okay. This is the complete equation. It's Navier-Stokes equation. Okay. So you have to use this equation in third and fourth. In third, it is given that divergence of V, you can calculate divergence of V is 0. So this whole term drops. This is 0. This one only this one. Okay. And then you find out the viscosity. But what did you find?
The calcium itself is 0. So
It has some very interesting conclusion. What did you find in equation 3? What did you find in equation 3? Some people found it. One person discussed with me as well.
that it is possible for every viscosity. It's possible for every viscosity because the Laplacian itself is 0. So if it's 0 times something, you can determine something.
This term was coming out to be equal to this term. This is anyway 0. Okay. This is anyway 0. Stationary fluid. So this term and you have 3 terms. So you find out that this was also 0 and these two are equal. So basically, so there are two conclusions here. One, somebody reached up to that or not. You found out that these two terms are equal.
You didn't have to see that those two terms were equal. You didn't have to do that. You just said, can we find viscosity? And the answer is no, because it's times 0. Any value that you put in, you can't isolate the value.
Okay, there is more to that. So first conclusion that because the Laplacian is 0, which will multiply with density, with viscosity, you cannot find it. Mathematically, you cannot find it. But there is a reason why I designed this question. If any fluid satisfies Euler equation, first two terms. Euler equation is satisfied only for the fluids where the viscosity is 0. So viscosity also has to be 0. That's a physical input. Do you understand that?
But actually, you can also derive the viscosity 0 because this has a curl and it never decays.
It has a
The curl.
curve. Where is curve?
You can calculate that the curl is not 0 and it never decays. That's also another.
So how do you find, okay, curl is non-zero, but it does not decay.
Yeah.
Until
But, okay, what do you mean by never decay?
Because you said that it's
Stationary. It's a stationary.
yeah, it's steady flow.
It's a steady flow, that's true. Your intuition is It's appreciable intuition, but this is not correct. The reason is that we will see in today's lecture. There can be situation where the flow is steady, but the viscosity is still low. There can be some additional force which is keeping the flow steady. Okay. We'll talk about it. This is about the lecture. Okay. Where were we? What was I saying? Okay. So the equation satisfied Euler equation, right? The fluid satisfied Euler equation. A fluid that satisfies Euler equation does not have viscosity. It's a non-viscous fluid. So when you do physical interpretation of this fluid, viscosity turns out to be 0. But you cannot determine mathematically. Physically, you find out it's 0.
If you're talking about things that are physical, this whole expression isn't physical.
Right.
Look at it. Velocity increases the farther you go away from the origin. It will go to infinity eventually.
System is not infinite. It can be inside a bottle or some finite given. You were not given boundary conditions. There's a constant here, okay, which is undetermined. Okay. So in third question, this last term was 0. What's his name? Adi. In fourth question, the divergence of V is non-zero. Right? But if you put xi equals 0 there, still you are left with one term. In the fourth question, the divergence of V is non-zero. Okay? That's an important point. So this term is non-zero. Okay? But if you take a gradient of that, it is still 0. Okay? Because let's say that. But anyway, I just want you to use the first incompressible terms. Okay? That was important. You can still assume that we don't use this term. You can use it, but it will just complicate things. So it does not have bulk viscosity. It does not have any contribution of the bulk viscosity either. In that case, you have to use the same equation. You have to find V dot grad V. In the same way you did in third question, and you found viscosity. What was the viscosity? $20? No. Okay. So I enforced, suppose this is 0. Now this disturbed couple of people, because if you calculate this is not 0. If you calculate V dot grad V, it is not 0. You can calculate. It may or may not be 0, I don't know. But still I said assume it is 0. Why did I say that? That is the part of today's lecture. Any questions in the solutions? You understood all them? Okay. Now it's just calculus. You have to find the gradient, etc. of that. Many people did. Okay. And that's number. And we'll talk about why did I infuse that it is 0. While mathematically it is not. written here for incompressible fluids. The Navier-Stokes equation is like this. Don't talk, please. Okay. So, given that there is a length scale of the system, suppose in last lecture we solved a couple of problems for viscous fluids. There was a flow between two parallel plates. There was a flow inside a pipe. Remember that? I think there was a problem in that as well, that we kept. Let's adjust that. I'll just remember. Okay. This was some solution for water, some fluid flowing inside a pipe. And I showed that A has to be 0. Remember the problem?
Yes.
We assumed that A has to be 0. So the solution was something like, in the middle of the pipe, V has to be finite. Okay? And then we got stuck. And we assume that this A is 0. If A is not 0, at R equal to 0, log R diverges. Okay? To prevent this from physical systems, you have to assume that A is 0. Okay? So when you take log R, this middle term is undefined and it diverges velocity, which is not physical. This is what I did not explain last time. I went and checked, but I forgot. Is it clear now? Good. Now we continue. So we solved a couple of problems. Flow inside a pipe between two parallel plates. Flow has a length scale, let's say L. Any flow. And you can think about a flow in a pipe, just to keep in mind. If it is length scale L, then what are the orders of magnitude of this fluid? Velocity. Suppose it's stationary, for simplicity, this term is 0. The first term, if the velocity is u, the fluid has a velocity u in a pipe, viscous fluid, and the length scale is L. That is moving in some length scale L. And the first term is the magnitude. Order of magnitude is rho u square by L. Last term is eta u or L square. Okay? We take the ratio of these two terms. Let's call this A and this is B. This ratio is called Reynolds number, and I will explain why. This is Reynolds number R. Okay? Reynolds number R. R. So ratio is simply rho u square over L. What is eta by rho? It's a kinematic viscosity. Yes. So there's a viscosity in the denominator of Reynolds number. There's a physical significance of this number. It will be important for next couple of lectures for us. When the Reynolds number go to 0, when R is equal to 0, what it means, what it signifies. This is Reynolds number. When is it 0?
When viscosity is massive.
Viscosity is massive. Okay. For high viscosity fluids, Reynolds number goes to 0. It's not just high viscosity. It is sufficiently small for these parameters to be balanced in such a way. So when is it 0? When suppose RL is much smaller than 1. It is a dimensionless parameter. If it is much smaller than 1, not 0. It is not 0. If it is much smaller than 1, means it is small. It simply means this first term is much smaller than the last term. Okay? So even if the first term is not 0, for small Reynolds numbers having fluids, this term can be ignored. Okay? This is why I said ignore this term. But technically it was not 0. It's very important confusion. What if the Reynolds number is high? Reynolds number is high for what? Reynolds number is 0 if the viscosity is very high or velocity is 0 if the fluid is not moving. It depends on the velocity of the fluid. It's not characteristic of the fluid itself. It depends on the parameters. So when the fluid is not moving, its Reynolds number is 0, or it is moving with very small speeds, okay, or its viscosity is larger, then its Reynolds number is small. So in that case, that's the specific condition where you can ignore this term. Okay? Now there are more interpretations of this.
Only when we get the viscosity, right? But how do you know it's larger than you? Or
Larger than?
you said when the viscosity is much, it's very large, we can say we can cross out this parameter. How did you know that U and L is smaller than eta?
It's important. That's what I said. It's not. It does not depend only on viscosity. It depends on all these parameters. When the combination of these parameters, we'll talk about a physical example. When given U, the density of the fluid, and let's say if it is a pipe given in a pipe. This Reynolds number is much smaller, then you can ignore this term. But let's go to other hand. Let's take a particular fluid. Let's take water. Best fluid that we know. For water, which parameters are constant here? Eta and rho. Okay. Water has a density, does not change. It has constant viscosity because it's internal characteristic of the matter. It has U and L. So now for water, Reynolds number is proportional to U and L. It depends on U and L. That's the water. For small Reynolds number, small velocities, and small cross section. For high Reynolds number, let's say the cross section is also constant for the time being. If the speed is high, if the water is accelerated, if the speed increases, that means Reynolds number is going down. Okay. What happens when you keep on increasing the speed of water? Nothing stops it from passing to the speed of sound as well.
So what do you think? Visual.
Okay. Huh?
Visual collapse. Visual collapse.
That's fine, but what do you see? What happens? Let's take a good example. You see the water from the tap. So turn it on very little so that you see a smooth tap water is falling down. So that's the classic example. Its velocity is increasing with distance and its cross section is slightly decreasing. So its Reynolds number is going up. If you do this, you have seen this. In the beginning the water is streamlined. Okay. But there is a time after which it becomes turbulent. You can go and check it today as well if you forgot about it. Water is smooth in the beginning. At some distance, it becomes turbulent. When the stream is falling at the ground, it's always turbulent. Remember that? It's not smooth indefinitely. Why it is turbulent? It means when the Reynolds number keeps on increasing, there is a threshold after which none of the equations work. Whatever we wrote. When there is no viscosity, Euler equation works. When there is viscosity, Navier-Stokes equation works. But when the Reynolds number is very high, this also doesn't work. So there is a limit to this equation. Water becomes turbulent. You see river which is passing smoothly and the river which is flowing fast. What is the difference? Difference is U and difference is R. And the fast flowing river is very turbulent. You are aware of that. That's the topic of our next lecture, turbulence. So this equation is not always implied. There is a limit to that. And what is the limit? Reynolds number has to be small. Small, when it is small, the equation is implied. When it is very small, you can ignore even the velocity.
Small compared to what?
Small compared to 1. When it is 1 or smaller than 1, we'll talk about the magnitudes. I'm not aware of the exact magnitudes where the limit changes. We'll talk about it in the next lecture. But when it is much smaller than 1, the velocity dependence is gone. When it is comparable to 1 or its significant magnitudes, then this equation works. Once it becomes higher, fluid becomes turbulent. So the tap water which is falling down in the beginning, which is streamline flow, it is explained by Navier-Stokes equation. But the moment it becomes turbulent, it cannot be explained. And it has not been explained in physics yet. We still don't know why turbulence works. It's an unsolved problem. Yes.
What does it look like when you do the mathematics and you try to force it to work with this equation when it should?
You try to force, your equations will predict, but your experiments will not follow.
usually when there's a physical law that breaks, there's something that happens in the math too. It's like dividing by 0 or square root of a negative number.
Not necessary. The assumptions break here. The inherent assumption of this equation is it's a streamlined flow. From the beginning, whatever we are assuming, it's a smooth flow. As long as it is streamlined, this equation works. It's not streamlined, mathematically it will always work. Put arbitrary values of that and you will get some solution, but practical, the world will not comply with your mathematical results. Okay? So that's what we expect. This is one significance of Reynolds number. It gives you a boundary beyond which none of the equations work and the turbulence starts. That's the next segment of our lectures from next one. The second implication is it's a dimensionless parameter. So all the parameters of the fluid, let's say velocity of the fluid, given velocity u at some point, for example in a pipe, velocity at the center is, let's say, u. The velocity is a function of Reynolds number. So all the principles, all the parameters, velocities, force, they scale with the Reynolds number because it's a dimensionless parameter. This we call principle of similarity. You take two fluids, water and oil. They have different viscosities, different Reynolds number, let's say. But because the Reynolds number is small, in that case, unless it is turbulent, your parameters of all the fluids behave in a similar manner and they are a function of Reynolds number. So in that regime, all the fluids behave in a similar manner. This is the principle of similarity. Okay? The physical factors including force and velocity, they depend on a function which is a function of Reynolds number. Okay. It's clear? So this is how we say that we are at the boundary of our discussion. And the moment Reynolds number increase, what happens to the system? There are two ways of finding. One theoretically, other one practically. Practically we know it becomes turbulent, zigzag and very bad. It's non-linear. But theoretically we still do not understand this phenomenon. It's an unsolved problem. Why the fluid suddenly becomes turbulent? So it's mathematical modeling is still people are trying to find it. So now we are at the last point of where our theory works. Whatever theoretical development we made, up to what point it is applied, we are at the last stage of that. And you have to always keep in mind it's the boundary is Reynolds number. And this was discovered by Reynolds. When the water falls down, you can assume it's like a pipe, right? There is no pipe, but water still has a width. It's a pipe of decreasing L, but increasing speed. And at certain length, it breaks. See, it no longer follows Bernoulli. Bernoulli theorem should always be, no. Bernoulli theorem will not be followed, but energy conservation will be followed. And that's the limit.
Will it happen in free space?
Hmm?
Will it happen in free space?
Yes. Your water stream which is falling down from the tap, it can fall in vacuum also as well. So when we talk in Reynolds number language, we talk about pipes, but it doesn't necessarily have to be pipes. It's just flow. If you, okay, there are many examples. You notice the smoke coming out of rocket. Once it comes out, it's always turbulent. Why? That's not just because of the viscosity, this reason, because it interacts with the wind as well. So, but it is turbulent. It has high Reynolds number, and also it interacts with wind, surrounding winds. This is what that may not be a good example. Water is a good example. So we can assume that water stream which is falling down, it is not interacting with the wind. Wind is tenuous, water is heavy, denser. 1 gram per cc, wind is density is negligible. So it will have to happen in the vacuum as well. Okay. That's the last topic, viscous fluids. Viscous flows past a solid body. So far we discussed very simple examples. Flow is in a pipe between two plates. Those were relatively simple examples. This is a complicated topic. It has very detailed derivation. So initially I thought I can skip this, but then I found a middleware. We can have a very good physical picturization of the process. Mathematically it is very cumbersome, so we can skip some steps because and I will put 2 of them in the assignments too, with just derivations and detailed calculations. But the important thing is we should have a good understanding of this. Did you do the experiment of dropping a metal ball in a viscous fluid and finding its viscosity?
Yes.
Yeah.
How did you find?
I think
If you remember something, we always forget things.
we said that we assumed that drag increases, the force of drag increases with velocity squared, and then we found a constant.
Force of drag, it's square, not square, it's velocity.
Okay, we found some equation that has gravity on this end and drag that depends on velocity on this end. We
Yeah.
found the point that it would be stable, and then we found the drag coefficient from that, and then we examined that.
Yeah. And then you equate it with mg, right?
Yeah, sure.
And you found out the mass, the size, density,
Those
and then you calculated eta. But where did this equation come from? This is Stokes law.
okay. We didn't go over this right.
This is not very smooth, it's very long derivation, but I still want you to have a feeling why it depends on eta, why it depends on r and v. So I decided that we can at least go over it and have a good physical picture of that. So what you did is you took a pipe, so we'll derive this force here. That's the motivation. So what you did is you took a pipe. I assume you did this. Okay? You drop a metal ball falling inside. What you noticed is in the beginning, its velocity increases because at t equals 0, its velocity is 0. If the velocity increases, accelerates, it has drag force continuously on that. After some distance, its velocity becomes constant. The water droplets that come from the clouds, they are like metal balls in air. They do not accelerate continuously. If you drop a stone, it will continuously keep on accelerating until it falls on the ground heavy. But the water droplets, which are pretty small, they accelerate, but then they obtain constant speed. So they always come at the constant speed of the ground. Okay. So we try to find out the drag force that is applied on its sides. Let's call this F drag, which we know you directly use it 6 pi eta RV. V is the terminal speed. This is what you call in the experiment. The speed when it becomes constant is the terminal speed. we derive this equation. It looks pretty simple and small example equation, but it's mathematically it's relatively cumbersome.
Is this how the radius of the sphere?
This is the radius of the sphere.
So this is a law specifically for spheres.
Yes,
Okay.
this is for sphere. It is correct for other shapes as well. If you put a plate,
Yeah,
It
up
is-
to some concept.
for plate it is same, but this constant will change. 6 pi instead of maybe 12 pi or something. I don't remember I derived this but long ago, but it has different coefficients for different shapes.
So it just means if you make the object twice as big, the force is going to be twice as strong. That's
Why?
the proportion because
Why?
it's proportional to R. That's what you're telling us intuitively.
Right. So intuitively why?
I don't know why it should be twice instead of 4 times or 8 times or some square.
Forget about that. Why it increases with R?
It has to increase with R because there's more stuff facing.
Surface, a bigger surface. Right? Good. And if velocity increases, force is more. Alright. And this equation is valid only when Reynolds number is not valid. If it is turbulent, nothing works. But we will consider even smaller, simpler example. We will go with the assumption that RL is much smaller than that. Okay. So you could check the experiment that you did and found value of eta. If you perform the experiment in certain manner, the velocity was higher, the Reynolds number was not negligible compared to 1, you may have ended up getting wrong value of eta. This is important. But because you know, so if you do the experiment in glycerine, you know glycerine? Like and honey. This assumption is always valid. Why? Because velocity will not increase slowly, it's very slow speed. When you put the ball, it falls down very slowly. If you put it in kerosene, I'm not sure, maybe the condition breaks. It will not become turbulent, but it will not remain in this condition as well. So this expression is specifically for small speeds, extremely viscous fluids. We should always keep the assumption in mind. So for small Reynolds number, the equation is now it automatically assumes that divergence of V is 0. Okay? It's incompressible fluids, which is true for liquids, not for gases. Again, you cannot use the same expression for gases. It may not be applying exactly in the same manner on water droplets.
What's the mathematical difference between liquids and gases?
You have
Viscosity.
other terms. Bulk viscosity will also come into picture. And I'm not sure what will be the solution, it will be complicated. So you have to assume many, even after putting a lot of assumptions, it is still mathematically complicated. Okay. So what we assume here for this condition, what does this imply? This implies that this term is 0. Or 0 means, 0 doesn't mean 0. This term is much smaller than this. This is why, and okay, one more thing. In the you obtained viscosity here. What was the value of viscosity? Something 20 rho or something, right?
Yeah.
So, in order to assume this is to be true, your density has to be accordingly. Okay? So, it's true only when the density is large, 20 rho. High viscosity. Alright. So now we have only this. So this is 0. And we have divergence of vapors. take the curl of this equation. This is 0. Why is this 0? Curl of gradient is 0. This is always 0. Okay? Eta goes in 0. And I can flip these operators. What is curl of V? We keep on teaching and we will keep on forgetting the past. What is curl of V? What is it? Circulation. What is it? Not circulation. What is it? Circulation is line integral. But it's del cross V is vorticity.
What does it represent?
C represents the circulation, but the circulation defined as gamma, it is a different quantity. So del cross is simply circulation. Basically what it is. Del square, let's call this omega. I don't know, did we call it omega? Circulation. Gamma was circulation. Omega was circulation we call gamma, but vorticity, what did you call vorticity? Maybe omega.
I don't think
We didn't give it any measure. Let's check.
I think in the homework there's something like
Huh?
in the homework you asked us to calculate the angular the curve.
Curl.
Yeah.
Okay, but not in the lecture.
I don't
No, curl was there, but did we give it to time? It's not important.
know. I think you did. Yeah, we called del cross V is vorticity, but did not give it a time. So, and this is vorticity. We wrote it as vorticity. Anyway, so this is the condition we have to derived. All right. But there is a problem here. There are two problems here. One, what is V? V is velocity of the fluid. Does the fluid has a velocity there? It's the ball which is moving. Fluid is not moving. This is one problem. What's the second problem? Anyway, how do you interpret V here? Velocity.
The fluid near the ball, near the falling volume, moves with the same speed as the ball itself.
That's correct. Another thing is, when you look from the ball's perspective, it feels like the fluid is going in opposite direction. This analogy does not always work. As I always say that moving fluid is not an inertial frame. Fluid is different. It's not like a moving car. It's different. But here it works. When the ball is falling down, it's seeing that the fluid is going away.
Why force?
Hmm?
Why it works here?
Okay. It works because it does not. When I say it does not work, I have to keep the principles general for terms of physics. Why it does not work? In general, the reason is, what's the difference between inertial frame and non-inertial frame? Inertial frame, two frames. If a train is moving with constant speed, it has inertial frame, unless it is not accelerated. Why it is inertial frame? Because there are parts in the train, literally the seat and the people who are sitting, all are moving with constant speed. Okay? In the fluid, there is nothing which is moving with constant speed. The particles are always moving around, so practically it's not an inertial frame. It just feels like it is constant speed. You go inside, no point is constant speed. This is why when you apply relativity, the problems come there. But I have to keep the things general so that you have an idea of that. Here that's not a problem. It's just how it sees that the fluid is moving across the direction. Take break.
Usually we take a
Okay, so let's proceed with this little bit, and then we'll stop at point, and then we'll take a small break. Okay. So assume that the velocity of the fluid is u at the walls. Okay. At infinity, rather infinity. Okay. This pipe has a length. When I say infinity, that means at the edges of the pipe, far from the ball. And we are inherently assuming that the length of the pipe is much larger than the radius of the ball, which is not visible in the picture. Just to keep things clear, it's far away. So at the far end, velocity is u, and the velocity changes along this r. The small v is the velocity of the fluid as a function of r. So we define v like this. We define a vector potential A. U is a constant speed at infinity if you do not ball seen from the ball. And V is changing. So we just defined that V minus U is some function of curl of some vector potential A. This ensures that divergence of V is equal to 0. When you take the divergence of this, curl divergence A is equal to 0. Take the divergence of this equation, it turns out to be 0, which allows us that velocity can be shown as a curl of velocity potential. I think we already seen this. Velocity potential.
yes.
A is velocity potential.
What can you remind what it's what did you define?
Define U, okay. Far from the ball, at the edges. U is basically the speed of the ball. The ball sees fluid is moving in opposite direction with velocity u. But it is not always u. Close to the ball surface, the velocity changes because it drags, so it slows down. The nearest surface is technically at 0 speed. Then it increases. And at far away, it is u, constant speed. Basically, it is the speed of the falling ball. Okay?
At the surface, it has to be equal to the speed of the fall. Right? Velocity of the fluid at the surface is equal.
In the frame of the ball, which is an inertial frame, at the surface, the velocity is 0.
Okay.
Not in the left frame.
Okay.
Curl of A. A is further defined as. Now, what is the nature of this A? A can only be a function of r along the distance.
But why do you want to have a velocity potential? This is a vector and that is a vector, so it doesn't simplify.
It does. This representation inherently assumes that the fluid is incompressible. What is the motivation? What is the purpose?
Because you want to say that the divergence of this is zero.
Yeah, divergence of V is 0. So now this divergence of V's condition has automatically come in the equations. Previously it was not there. No? You can go in many ways, but your purpose is in the simplest mathematical way, you have to reach up to the target of finding what is the force. Okay. Now, A is further defined like this. Yeah, this is not U, this is R. Because A is a function of R, there is a function F. F prime, it's a gradient, it's a derivative. Function of R and the cross product of the N, which is N, and this is R. Okay. N is just the vector coming out of the center of the sphere. And in this spherical coordinates, at the center of the ball, it is origin. So everything is in the frame of ball itself. Only then you can say the fluid is moving, otherwise fluid is not moving, or not moving with speed u. So V becomes u plus del cross u. Now we know u is a constant. U is a constant vector. So when it is a constant vector, it can be represented as now we have to find this del cross v. When I find del cross v, what will be the first term? What will be the first term? If I do del cross v, is it del cross u?
Sure, yeah, it's
What is del cross u?
0.
0. Okay. Fluid is just going in linear direction. It doesn't have a curve. So you are left with only this term, which is curl of. It will become even nastier than this. Okay. But you just have to keep the physical picture in mind. That's the motivation. Now, identity. Del of, let's say, use this identity. del dot. We have used this before. This term is 0 in our case. Why? No. Divergence of u is 0. Velocity terms have divergence. This term is 0. So you only have, this can be written in this form. But there are two curls here. We have one curl left here. There's minus sign, so this minus sign goes to the other side. Minus del square. Okay. Yes. We have defined A equals F prime. This is F prime, okay? So F prime will continue. So V becomes U plus this F prime is basically grad of it. Once it becomes grad f, now it doesn't have F prime. It's F prime only up to this time. F and back. Del squared curl of grad f u. Del squared del f. Okay. So now, if you remember the previous equation, we found out del square this was 0. Okay. Now we found out curl v. There's more del square there. Curl v is a del square. Del square becomes del 4. Okay. Now, double Laplace operator. Okay. Now, u is constant, right? Laplace operators also do two types: scalar Laplace operator and vector Laplace. Because it's a vector here, u is a vector. But because u is constant vector, it goes away. So what you are left with is It's easy to find out density of time. Now the purpose is to find what is f.
Know about functions have Laplacian equals 0.
Hmm? Yeah, you have to find that function for which this is 0, which is, we are working in spherical coordinates, right? Not in Cartesian. Can be written like this. So double Laplacian comes out like that in spherical coordinates, but you're still left with one Laplacian inside. So what you need to do is solve this. Okay? You can write it, solve this. This r square goes away, then integrate it twice, okay? And then you get del square r. Then you put the operator again, solve it again, repeat the process, and get f. This I will give you in your assignment. You don't solve it here. A plus A and B are two constants. So in the assignment, when you solve this double Laplacian, find the value of f, which I have written there. Then what you will do? What we do with f? What was the expression of v? We use f to find out v. Okay? Put the expression of f in the expression of v here, and find out what is the value of v. It's just take the gradient and the curl and then find out v. So v comes out to be this is the final expression. If you solve that, put it in the expression of v, you find out this expression of v, which is understandable. What do you take out from here? These two terms are positive. The velocity decreases. Its velocity u is maximum velocity, far away, infinity, and it increases with distance. But it is always less than this. It depends on the parameters you put here. Now you project it along r and theta in spherical coordinates, and you obtain Vr and V theta. That I will also write it directly. We don't do all the calculations because first of all I just wanted to avoid this problem, but it's better to have a physical insight. You break this in spherical coordinates, you get this Vr and V theta. And I will not give this derivation exam. This will not come, but its physical interpretation will come. We just want to have a feel of the problem. Even without turbulence, assuming that Reynolds number is much smaller than 1, still the problems become complicated. Fluid dynamics is not very straightforward. Okay. Now we are Navier-Stokes equations without considering the first term, which is gradient of P equals right, which is the simplest form you can assume. Make it complicated, then it will be even harder. So you found out V, okay, by the double square. Again, you have to find this Laplacian of V. It's a vector Laplacian. You always have to understand the vector Laplacian and scalar Laplacian is different. The vector Laplacian is
Where did B go in those in the spherical when you substituted it? Here does B and here
it went in boundary conditions. So when I write the notes, I will say. So what you assume is the velocity at infinity is u, at the surface it is 0.
yes.
Put the boundary conditions, solve it properly, then you say these two. So one constant is taken out, but you can, the second has to be eliminated as well. Okay, so what you do is take V, put it here, solve it, gradient of P, integrate it, you found pressure. Okay? So I'll write the final expression. Pressure turned out. And you put the two boundary conditions. One is at the cylinder, other one is at the boundary of the sphere. Two boundary conditions, two constants, everything vanishes. Now we need to calculate force. So once you know the pressure, how do you calculate the force?
Minus gradient.
How do you calculate the force? Force is integral of pressure into area, integrated over area. But this is not very straightforward. The difference between non-viscous fluid and viscous fluids is that only pressure is not enough. You have to calculate the viscous stress tensor too. We saw it in the general equations. Pressure is not just pressure. It has terms of sigma, that is viscous stress tensor. So we just have an idea how the velocities are put and how do you calculate the force in viscous case. So force is here. What is F here? F is the area of the sphere. Bounded area. Now this is sigma RR. Previously we assumed sigma X, Y, etc. You have to consider two stress tensors, sigma and then put it here, put the expression of pressure there, and integrate it over the surface of the sphere. Okay. That's it. Let's just finish it. Okay. Then we finish the lecture. Okay, 10 minutes.
Wait, so no break today, just finishing lecture?
Because if we anyway it is very cumbersome. If you take a break in between, anyway you're not understanding anything. If you're understanding 5%, you will not understand 5% even. The reason being, my purpose is not to have you a feeling of mathematical details. It just needs to have a feeling of how the force is applied on that and how you use the simple expression, the expression for calculating viscosity, how it comes out.
I understand, but if you want to look at the terms and give us a solution for them, then maybe we can do that after we're burned out. Because right now I don't think if you take like 20 minutes and they come back and show us the equation behind this.
We just need 2 minutes after that.
Sure.
So I'm not going to derive all of that. I did not derive anything anyway. Okay. So we calculate this sigma terms, which are just derivatives of velocity terms in spherical coordinates, integrate it over R, you obtain this expression. Now, if you want to calculate, I have derived it, but if you want, I can include everything in the notes, but that is not very necessary. This will not come in the exam. Still, I wanted you to have a feeling of it. So, what's the process? How did we do that? We defined a velocity potential in terms of some function f. Then we calculated f, solving the double Laplacian, and calculated the velocity potential, velocity factors, and the pressure from the Navier-Stokes equation. Putting the pressure and calculating all the stress, you put it there and you get this. Okay? So in the notes you will have these terms. I'll just write it, but it's not very important. You should have an idea how we calculated the force. Now, physically, you can understand the picture of this. You are burned out. I am burned out more than you are talking continuously. So we can understand this. This force increases with viscosity, increases with radius, increases with velocity. Now this is very, very smooth. Single power of all the parameters. The problem is the nature is not that smooth because we put many assumptions here. If you go in the literature, people have worked hard. There are very detailed papers to find the general values of that. Second thing, we have assumed that velocity is constant. U is constant. This is counterintuitive. If you shoot a sphere in a viscous fluid, what will happen to the velocity? We discussed about it. Can it have constant velocity?
If there's a force counteracting that.
There should be additional force. If there is no force,
No, it will slow down.
it will slow down. Why it will slow down? Because viscosity is a dissipative factor. It takes energy. It eats up your energy. So you have to give some energy to the system. So how did you find out then in the experiment? This assumption is very strong. It cannot be broken. When you put the constant, because you see this U came out in many integrations because it was strictly constant. It cannot work in accelerating or decelerating sphere. So the thing is, how did it work in the laboratory?
Extra force.
Which force? In the laboratory, what you did? You dropped the ball. It reached constant speed. How did it reach constant speed? There's a gravity which is always pulling it. So you have to give some extra force to counter that viscous dissipation. Right? Whatever viscosity is eating from the system, gravity is giving you, and that makes it balanced. So indeed, when the sphere falls at constant, that you can check, right? You can check in the glycerine's tube. After certain speed, its velocity remains constant. That means many crude assumptions that you put here all work for water, for glycerine and the sphere. Okay? These are justified. So only in that case you can find it out. Otherwise, in a simple system where you shoot the ball the velocity constant, it's not possible. Otherwise, you give some extra force. Fortunately, we have gravity which works wonderfully. Okay. I think we stop it here. And okay, so we finished viscosity. We dealt with many examples. There were some simple examples that we dealt within last lecture. Here we dealt with the complicated one, but still, I think you got the physical idea. Okay? That's the most important thing. And I can see when you are solving the problems, there are problems with the gradients and curls, it means divergence, etc. So when I give you the problems in the assignment, are you doing it yourself? In assignments, the problems that I give you, if you solve the problems yourself, the problem that I gave, besides there were some mistakes, okay, I'm sorry for that, but the calculus was straightforward. I just wanted to see if you do it yourself or not. So please do it yourself, the assignment problems. It will help in the exam and also in general understanding. Okay, we finished viscosity. Next, what if Reynolds number are not much smaller or smaller? Whatever we studied, everything breaks down, nothing works. Then we are in the regime of turbulence. So stepping up with more and more complicated system. Turbulence is also a dissipative process. Viscosity is a dissipative process because a constant moving flow and the particle slows down. What about turbulence? Take a bucket, stir it fast. If you stir slowly, what happens? You will still feel the drag force on the stick, right? That is viscous force. But if you stir it faster, you feel enormous drag force, and the flow becomes turbulent. That is coming from turbulence. Turbulence also eats up energy. So if you take a like fish tank, stir it very fast and then leave, everything is turbulent, but slowly everything becomes still again. Why? Turbulent eats up energy. It cannot be maintained. Energy has to be given. Who is giving energy to the river? River is flowing. Gravity. Gravity is continuously giving the energy. And gravity is making your tap water to become turbulent after some distance. So keep these examples in mind, and we will try to have some mathematical intuition of turbulence, with the caveat that it is not yet fully solved. Okay? Thank you.
What is the question of turbulence if it isn't fully solved? Is that $1 million question?
Please. Which didn't come back. No, for turbulence. That is for David Stokes. It is also not. Analytically, it's not solved. But you can solve it numerically. We don't even know because that's no linear process.
You just have statistics.